Grounding one corner or line to ground fault of a delta-connected transformer winding leads to an unbalanced voltage distribution. The reason this happens is that the grounded phase now operates at 0 volts to ground, while the two other phases remain interconnected to the balanced three-phase system. As a consequence, the voltage experienced across the other two ungrounded phases goes up by a factor that is the square root of 3, or approximately 1.732. This increase occurs because the system's total voltage is constant and it has to be distributed across the remaining phases. Now let's delve into the basic insulation level or BIL increase. The BIL represents the voltage level that the transformer winding can endure without any insulation breakdown. When we ground a corner of the tertiary winding, we are essentially creating a pathway for an increased fault current to flow through the winding. This elevated current can lead to arcing and damage to the insulation. To safeguard against insulation failure, the BIL of the tertiary winding must be raised to manage the increased fault current effectively. This is usually achieved by using thicker or high-quality insulation materials. Now let's consider the necessity of complying with the increased BIL. If the transformer is situated indoors and linked to underground cables, adhering to the increased BIL requirement hinges on the particular regulations and standards that are applicable in your area. Typically, the elevated BIL requirement is put in place to shield the transformer from lightning surges and other temporary overvoltages that may happen on overhead lines. However, if the transformer isn't exposed to these overvoltages, then the increased BIL might not be needed. Now let's talk about reference materials. Firstly, IEEE Standard C37.91 2011, which serves as a guide for protecting instrument transformers. Secondly, IEC Standard 60076.1, which covers power transformers in general. Thirdly, SIGA Technical Brochure 348, which is about high voltage direct current or HVDC systems. To reiterate, grounding one corner of a delta-connected transformer affects the voltage distribution. The grounded phase becomes 0 volts to ground, with the other two phases remaining connected to the three-phase system. As a result, the voltage across the other two ungrounded phases goes up by a factor of approximately 1.732. The BIL is the voltage that the transformer winding can withstand without insulation failure. When a corner of the tertiary winding is grounded, it makes a path for a higher fault current to flow through the winding. This higher current can cause arcing and insulation damage, and to prevent insulation failure, the BIL of the tertiary winding must be increased to withstand the higher fault current. If the transformer is indoors and connected to underground cables, the need for complying with the increased BIL requirement depends on the specific regulations and standards. The higher BIL requirement is intended to protect the transformer from lightning surges and other transient overvoltages that can occur on overhead lines. However, if the transformer is not exposed to such overvoltages, then the increased BIL may not be necessary. Firstly, refer to IEEE Standard C37.91 2011, Guide for Protection of Instrument Transformers. Secondly, refer to IEC Standard 60076.1, Power Transformers General. Thirdly, refer to SIGA Technical Brochure 348, High Voltage Direct Current or HVDC Systems. The grounding of a corner in a delta-connected transformer results in an altered voltage landscape. The grounded phase reaches 0 volts relative to the earth, while the remaining pair of phases maintain their links to the three-phase framework. Consequently, the voltage levels across these two ungrounded phases escalate by roughly 1.732 times. This escalation is a direct consequence of the constant total voltage of the system, which needs redistribution among the surviving phases. Now let's discuss the importance of the basic insulation level. The BIL is the voltage threshold that a transformer winding can endure without compromising its insulation integrity. When we ground a corner of the tertiary winding, we open a channel for intensified fault current to traverse the winding. This heightened current carries the potential to trigger arcing events and inflict damage upon the insulation. To preempt insulation breakdown, it becomes crucial to elevate the BIL of the tertiary winding, thereby empowering it to effectively manage the augmented fault current. This enhancement is typically realized through the deployment of thicker insulation materials. Now, let's shift our focus to the necessity of aligning with the augmented BIL. In scenarios where the transformer is sheltered indoors and interconnected via underground cables, the imperative to adhere to the increased BIL hinges upon the specific regulations and norms governing your locale. Predominantly, the rationale behind the heightened BIL is to fortify the transformer against lightning-induced surges and other transient overvoltage occurrences that are prevalent on overhead power lines. Conversely, if the transformer remains shielded from such overvoltage incidents, the heightened BIL might not hold the same level of necessity. For reference, consider these 3 points. Firstly, the IEE standard C37.91/2011 offers guidance on safeguarding instrument transformers. Secondly, the IEC standard 60076.1 lays out specifications for power transformers in general. Thirdly, the SIGGR Technical Brochure 348 delves into the intricacies of high-voltage direct current or HVDC systems. Let's look at grounding a single corner or line to ground fault on a delta-configured transformer winding creates an imbalanced voltage scenario. The grounding action forces a grounded phase to a 0-volt potential with respect to the earth, while the other two phases maintain their connection to the overall three-phase system. As a result of this arrangement, the voltage present across the two ungrounded phases rises by an approximate factor of 1.732. This increase is attributed to the fact that the system's overall voltage remains consistent, necessitating its redistribution among the remaining phases. Next, let's consider the basic insulation level increase. The basic insulation level denotes the maximum voltage magnitude that a transformer winding can withstand before experiencing insulation failure. By grounding a corner of the tertiary winding, a pathway is established for an augmented fault current to circulate through the winding. The presence of this elevated current introduces the risk of arcing and subsequent damage to the insulation. To avert insulation-related failures, it becomes crucial to elevate the basic insulation level of the tertiary winding, enabling it to effectively handle the increased fault current. This objective is typically achieved through the utilization of either thicker or improved quality insulation materials. Lastly, let's focus on the necessity of adhering to the increased basic insulation level. In instances where the transformer is positioned indoors and linked via underground cabling, the imperative to comply with the augmented basic insulation level stipulation hinges on the particular regulations and benchmarks that govern your specific location. In general, the intent behind the more stringent basic insulation level mandate is to safeguard the transformer against transient overvoltages such as lightning surges that may manifest on overhead power lines. However, in scenarios where the transformer remains isolated from such overvoltage events, adherence to the increased basic insulation level may not be deemed essential. Firstly, IEE standard C37.91/2011, providing guidelines for the protection of instrument transformers. Secondly, IEC standard 60076.1, outlining general specifications for power transformers. Thirdly, SIGGR Technical Brochure 348, delving into the intricacies of high-voltage direct current or HVDC systems. Now let's talk about the delta-connected transformer winding's voltage distribution. It will change when one corner or line to ground fault is grounded. The grounded phase is forced to 0 volts against the earth, and the other two phases stay connected to the system. So, the voltage on the other two ungrounded phases rises by about 1.732. This is caused by the system's constant voltage that must be split across the remaining phases. When a corner of the tertiary winding is grounded, a higher fault current path will be made, and it's called the basic insulation level increase. The basic insulation level is the voltage the transformer winding can handle before its insulation fails. Insulation damage and arcing can occur with the higher current. You have to increase the tertiary winding's basic insulation level to prevent insulation failure so it can handle the higher fault current. This is usually done by using thicker insulation materials. When a transformer is indoors, the need to follow the increased basic insulation level rule hinges on the specific standards in your location when connected to underground cables. The higher basic insulation level rule is to protect the transformer from lightning and other transient overvoltages on overhead lines. But if the transformer is not exposed to overvoltages, the increased basic insulation level might not be needed. IEEE Standard C37.91 2011 Guide for Protection of Instrument Transformers, IEC Standard 60076.1 Power Transformers General and SIGUR Technical Brochure 348 High Voltage Direct Current or HVDC systems are some references.